Hello students, welcome you all to the next lecture of our interference series. In engineering physics series, we have started that interference, where in first lecture we discussed about what is interference, what are the types of interference, and also we derived the fringe width or the conditions for fringes in Young's double slit experiment. So I think you must have gone through that video, and if you have any doubts regarding that also, you can let me know in the comment section. Today, as you know from the thumbnail, we will discuss about the thin film. How interference takes place in thin film, we will discuss. So before going to that, we have to first discuss about what is reflection of wave. Already we know that what is reflection. Bouncing back of light from any surface is known as reflection. Then how the wave react when mediums are different? If we consider optical rarer medium or optical denser medium and wave is traveling in any one of them and reflected from the other type, is there any difference between them? If there is any difference, then what is that difference? Then we will first discuss about that reflection part. So when we consider a ray of light or any type of wave, if we consider, and wave is traveling from optically rarer medium and here optically denser medium. Whenever any wave is traveling like this, the incident beam, okay, wave is traveling the incident beam and reflected by a denser medium, is there any change, or what is the change? Then we have to calculate. Again, another case we will discuss, where if the wave is traveling or incident wave is moving in denser medium and reflected by means of a rarer medium. So always remember, whenever wave is traveling in optically rarer medium whose density is less as compared to the second medium, then after reflection the wave completely gone out of phase. Out of phase means there is a change in phase. Phase difference will change by 180 degree. Pi will be the phase difference. Whenever there is a phase difference between two waves is 180 degree, they are said to be out of phase. If the phase difference is 0 degree, they are said to be in phase. So always remember, when wave travels from optically rarer medium and reflected by means of a denser medium, always there will be a phase change of 180 degree. But if it travels through denser medium and reflected by means of a rarer medium, there is no phase change. So when we consider a wave traveling in rarer medium and strikes a denser surface and reflected back, here you will find out the wave completely opposite to the previous one. Here positive, negative. So here it will be positive first, then negative. So here phase difference is 180 degree. But when we consider denser to rarer, there is no change. The wave will be same as the incident wave. Incident wave and reflected wave both will be same when wave travels in denser, reflected by rarer. But incident wave and reflected wave both will be out of phase or opposite when ray travels in rarer and reflected by means of a denser medium. I hope this thing is clear. We have to use this concept in interference through a thin film. So next, the main part, interference through a thin film. So we consider a thin film first. Let a thin film is there. A thin film is there. So thickness is T. And let refractive index is mu. Because if we consider soap bubble or any oil, if we consider a small layer whose thickness is T and refractive index is mu here. When ray of light falls, let a beam of light is coming. Always we know that when a beam of light falls on a reflecting surface, a part of light, if it is a refracting surface also, a part of light will reflect, a part of light will refract. If we see the glass in the window, you can see the other side. That means light is refracting, light is traveling from one medium to other medium, that is air to glass. Also you can see the inner view, or you can see the inside view of the room. That means a part of light is reflecting, maybe 10%, 20%, but a part of light is reflecting and a part of light is refracting. So whenever we consider a beam of light falls on a surface, we consider here thin film as the refracting surface. Then a part of light will reflect and a part of light will refract. So here this is the reflected beam R1 and a part of light. If this is the perpendicular, then if we consider optically rarer to denser, always we know that this is air This side is also air, and this medium is having refractive index of mu. And already we know that when ray of light travels from optically rarer to optically denser medium, rarer medium means here we consider air, denser medium means that thin film material, always it bends towards the normal. So if you plot the normal, then this ray of light will bend slightly towards the normal. I hope this point is clear. Then here also a part of light will reflect and a part of light will refract. So these things will continue. This is R2. Again here a part of light will reflect, part of light will refract. These things will continue till the intensity will be 0. So here we consider two rays, R1 and R2, where R1 is the reflected beam from the first surface. R2 is what? When ray of light travels through the medium, that means that thin film, a part of light will reflect it and this part again refracted. So now we have to find out the interference between R1 and R2. Let we give some name to the surface or the points. Let this point is A, this point is B, this is C, A, B, C, and this midpoint, let this midpoint is D. So always we know that to calculate interference, we have the conditions for path difference. Path difference must be even multiple, path difference must be odd multiple according to constructive and destructive, already we know. So here our aim is to first calculate what is the path difference. Once we calculate path difference, we have to use that to in that given condition. So the path difference means the extra distance traveled. When we are calculating the R1 and R2 are the ray, we have to calculate the path difference between R1 and R2. So you can see here R1 is completely traveling in air, but what about R2 here? R2 is traveling from A to B, B to C inside the medium having refractive index mu, and then it travels in air. So path difference, when the ray of light travels from A to B and B to C, during that time this ray will travel some distance. Let that distance is this much. We name that as E. Let this is the distance E. Clear about that? How we will get this distance? Now we know that velocity of light in the given medium, velocity of light in air. Here we know that C, here we know that V, because mu equal to C by V. If this takes B to A to B and B to C, let the light takes 2 seconds. During 2 seconds, this much of distance will be C into 2. So this distance we can calculate, and here will be always perpendicular. Now if this is angle of incidence, this will be angle of refraction, and if this is angle of refraction, this angle will be R also, this is also R. So path difference, first you have to find out path difference between R1 and R2. R1 and R2 path difference is the extra distance traveled by R2, which is equal to A, B plus B to C inside thin film, minus during that time R1 travels a distance A to E in air. Clear? This is the path difference. Path difference equal to A plus B plus AB plus BC, where AB BC distance is inside the thin film and AE is air. When we compare these two distance, we have to include the medium, because two different rays R1 and R2 are traveling in two different medium. If we consider an example of, for example, we consider two athletes. One is running in the proper track, another person or another athlete is running in a sea beach, in a sea beach where sand is there. We cannot compare their speed there. We cannot compare their speed because both the athletes are given two different surrounding conditions. So when both are given the same surrounding conditions, then you can compare whether first athlete is faster than second or second one is faster than first. When same surrounding conditions are given, then you can compare. Similarly here also, since this distance A to B and B to C is traveling in refractive index whose medium refractive index is mu, and this distance is traveled in air whose refractive index is 1, we cannot subtract directly. For that region we have to multiply For that reason, we have to multiply mu here. So the path difference will be AB plus BC. Either we have to consider both AR or we have to convert both into medium. So AB plus BC into mu minus AE. Now both we converted into AR. So this is the path difference. Now we get the formula for path difference. Now our work is to find out the expression for AB, BC and AE. Clear about that? So here in the triangle A, B and D, this triangle. Clear? This triangle. Let me make that triangle here. This triangle is like this. A, B, D. This thickness is T. Here angle R. Here you can see A to B, B to D. This distance. This is R and this thickness is T. Now we have to calculate what is AB. In this triangle, what is cos R? Cos is always equal to base by hypotenuse. So base is here, this distance BD divided by hypotenuse is AB. But BD is given, what is that is equal to T, small t by AB. So AB is equal to T by cos R, or you can write T sec R. We get AB. Clear? Our aim is to calculate AB, BC and AE. Now we get AB. AB equal to T sec R. T into sec R. Then what is BC? Then what is BC? From figure you can see A to B is equal to B to C. So no need to derive again. You can directly write. AB equal to BC equal to T sec R. Now our work is to calculate AE. We have to calculate AE. If this is I, this must be I. Clear? This must be I. So now focus on the triangle AEC. AEC. Let me draw that in the next page. Triangle AEC. This is I. So in this triangle, what is sin I? Sin theta is always equal to perpendicular by hypotenuse. So here in this triangle, this is the hypotenuse. So perpendicular will be AE. AE by AC. We need AE. So AE equal to AC sin I. And what is AC? AC already you can calculate here. A to C distance is 2 times of AD. 2 AD. So A equal to 2 AD sin I. Here we get R, here we get I. If we use Snell's law, from Snell's law we know that mu equal to sin I by sin R. So sin I is equal to mu sin R. So here you can directly write down this is equal to 2 AD. AD we will calculate. In place of sin I we can write down mu sin R. Clear? So A equal to we get 2 AD mu sin R. Now our aim is to calculate AD. So from where we can calculate AD? From this triangle you can calculate AD. Clear? AD, if you calculate tan theta in triangle ADB, tan theta is always equal to perpendicular by base. So perpendicular is AD, base is BD, equal to AD by BD. So AD equal to BD tan R, and BD is nothing but B to D distance. This is the thickness T tan R AD. Now we have all the values. We have the values for AB and BC. Now we have the values for AE, and here in that formula we have AD. Now we calculated AD. So in next page I am writing what will be the new expression for AE. We get AE equal to 2. Here you can see 2 AD. AD means here T tan R. So 2 tan R, 2 tan R into, we have multiplied mu sin R, mu sin R. Clear? This is sin by cos. Now path difference. Now path difference is AB plus BC into mu. AB plus BC into mu. Path difference formula, again I am writing x equal to AB plus BC into mu minus AE. So AB equal to T sec R, BC equal to T sec R. So you can write 2T sec R into mu minus AE, already we calculated AE, 2 tan R mu sin R. So you can take common. Clear? If we take common, 2T tan R, I just left T tan R. Okay, AD equal to T. There will be a T. 2T tan R. Okay. So this will be 2T. We can take common 2T. Mu also you can take common. So in bracket we will have sec R minus tan into sin. Tan into sin means sin square R by cos R. So this is 2 mu T. In bracket this will be 1 by cos if we take common. Sec is 1 by cos. 1 minus sin square R, and 1 minus sin square theta is nothing but cos square theta. So path difference is 2 mu T in bracket divided by cos R into cos square R. So x equal to 2 mu T cos R. So this is the path difference between the light R1 and R2. R1 and R2 we get. Now our aim is to find out the conditions. So conditions we can easily find out by equating to the formula, because we know that for constructive path difference must be even multiple of lambda by 2. For destructive path difference must be odd multiple of lambda by 2, where n starts from 0, 1, 2, 3 super. Here also n starts from 0, 1, 2, 3 and so on. One more important thing you have to remember here, this is the extra distance traveled by the light R1 and R2 between the reflection and refraction, because R1 is reflected, R2 is refracted here. But from reflection of light we know that when ray of light travels in optically rarer medium reflected by a denser medium, so there will be a path difference of lambda by 2. If phase difference is 180, corresponding path will be lambda by 2. So the total path difference here will be, so the total path difference is here, total path difference is 2 mu T cos R. This is the extra distance traveled by R2. R2 is traveling extra distance, this distance, and during this time there will be a path difference of lambda by 2. So the difference will be the total path difference minus lambda by 2. For example, during that particular time the light travels A to B, B to C, let 100 meter, and during that time A from that A, light travels A to E. Let during that time, for an example, I am giving A to B, B to C is 100. During that time, A to E is traveling 20. We cannot say the path difference is 100. The path difference will be 100 minus 20, which is equal to 80. This is the difference between them. Same thing we are applying here. We first calculated the distance traveled from A to B, B to C. During that time, this light is also traveling this distance, where a path difference will be lambda by 2 due to reflection. So the resultant path difference will be this much. Now our aim is to just equate. This is equal to n lambda. So you can directly write for constructive 2 mu t cos r minus lambda by 2 equal to n lambda. So 2 mu t cos r will be minus lambda by 2. Here we can add. So this will be 2n plus 1 lambda by 2. So this is the condition for constructive. Constructive interference. Now we have to find out condition for destructive. Already we have the equation 2 mu t cos r minus lambda by 2 equal to 2n plus 1 lambda by 2. Same thing we have to do, minus lambda by 2 we can to take to other side. So this will be 2 mu t cos r. If we take to this side, this will be 2n plus 2 whole into lambda by 2, where n starts from 0, 1, 2, 3 and so on. N starts from 0, 1, 2, 3 so on. You can directly write 2 mu t cos r equal to n plus 1 lambda by 2, where n starts from 0, 1, 2, 3 and so on. Here also one thing you can do, you can also write 2 mu t cos r equal to, if you take 2 common, you can cancel here. So this will be, you can write n lambda. You can write like this, n lambda, but the condition will change here. When you put n equal to 0, result will be 1. When you put n equal to 1, result will be 2. The number starts from 1. So here you can write n equal to 1, not 0. 1, 2, 3, 4 and so on. If you write n plus 1 into lambda, then n starts from 0. If you write n lambda, then n starts from 1. So here we get the condition for constructive, here we get the condition for destructive. That's all for thin film. This is very important derivation. If you face any difficult, let me know and do some numericals. I have some numericals for you. Practice all these numericals. Okay. I have given some numericals from Young's double slit and thin film. Practice all these numericals and let me know in the comment section what answer you are getting for question 1, 2 and 3. Question number 1, question number 2, question number 3. So we will meet in the next video where we will discuss about Newton's rings. Thank you.